This is Euclid Book 10, proposition number 114. And for these final two proofs, I'm not going to draw any fancy squares or show you any ratios or anything like that, because I figure by now you probably should be able to do this all by yourself. So hopefully that's what you'll do. I'm just going to go ahead and read this to you and see if you can catch on, all right? If an area be contained by an apotome and the binomial straight line, the terms of which are commensurable with the terms of the apotome and in the same ratio, the side of the area is rational. For let an area, the rectangle ABCD. Now what you're going to do is you're going to construct a rectangle, two sides of which are going to be the length of AB, the other two sides of which are going to be the length of CD. Okay? And they're going to be contained by an apotome AB, this is an apotome right here, and a binomial straight line, which is CD. So this is a binomial straight line, this is an apotome. And let CE, right here, be the greater term of the latter. Okay, so this line is actually going to be bigger than this line. Okay. Let the terms CE and ED of the binomial straight line be commensurable with the terms AF and FB. So, in other words, CE is going to be commensurable with AF, and ED is going to be commensurable with FB. Okay? And they're going to be in the same ratio. And let the side of the rectangle ABCD be G. Okay, so when you draw the rectangle ABCD, one of the sides of that rectangle is going to be the length of G. Okay? Now we're going to claim that G is rational. Now we're going to prove that. For let a rational straight line H be set out. H has been drawn. And to CD let there be And to CD let there be applied a rectangle equal to the square on H, and producing KL as the breadth. Okay, so we're going to make a rectangle, and the area inside of that rectangle is going to be equal to the square on H. Now what we're going to do is we're going to take the line H, we're going to turn it into a square, and all four sides of that square are going to be the length of H. Okay? And the area inside of square H is going to be equal to the rectangle that is applied to CD. Okay? And that rectangle is going to have KL as the breadth. Therefore, KL is an apotome. Let its terms be KM and ML. So KM is one term, ML is the other. And they're going to be commensurable with the terms CE and ED. Okay, so KM is going to be commensurable with CE, and ML, which is this one right here, is going to be commensurable with ED of the binomial straight line in the same ratio, which is by Euclid Book 10, proposition number 112. But CE and ED, this one here and this one here, are also commensurable with AF and FB and in the same ratio. Okay? We already established that earlier. Therefore, as AF is to FB, as this is to this, so is KM, which is this, is to this. One more time. As this is to this, so is this is to that. Therefore, alternately, as AF is to KM, so is BF is to ML. Therefore, also the remainder AB, which is this, is to the remainder KL, which is this, as AF, which is this, is to KM. And that's by Euclid Book 5, proposition number 19. But AF is commensurable with KM. This is commensurable with this. That is by Euclid Book 10, proposition number 11. And as AB is to KL, as this is to that, so is the rectangle CDAB. Now, hopefully you constructed that rectangle CDAB. Okay. Now we're going to construct another rectangle, two sides of which is going to be CD, and the other two sides are going to be KL. Okay. So we're going to construct another rectangle, two sides CD, two sides KL. Okay. So, as the line AB is to the line KL, so the rectangle CDAB is to the rectangle CDKL, which is by Euclid Book 6, proposition number 1. Therefore, the rectangle CDAB is also commensurable with the rectangle CDKL. Okay? So, let's say that again. The rectangle CDAB is commensurable with the rectangle CDKL. That's by Euclid Book 10, proposition number 11. But the rectangle CDKL is equal to the square on H. Okay? Therefore, the rectangle CDAB is commensurable with the square on H. But the square on G, now you're going to draw a square. And all four sides of that square are going to be the length of G. The area inside of the square G is going to be equal to the area found in the rectangle CDAB. Okay? Let me say that again. The area inside of the square on G, in other words, we took G, we turned it into a square. That area is equal to the rectangle CDAB. So the area inside of CDAB is going to be equal to the square on G. Therefore, the square on G is commensurable with the square on H. Okay? But the square on H is rational. Therefore, the square on G is rational. Therefore, the length of G is rational. And it is the side of rectangle CDAB. Therefore, and it is made manifest to us by this also that it is possible for a rational area to be contained by irrational straight lines. And that is the whole proof. One more proof to go and we are done with Euclid Book 10. Then we can move on to some more exciting stuff. Alright, I will tell you more in a future video. Stay tuned.